I'll give the first talk this morning about digital pathology and its importance as an omics data layer. This event is essentially sponsored by two companies, Pathomation and Histogenics, for which you thank them somehow. And then my financial disclosure is that I'm actually involved with both of them. I'm co-founder of Pathomation, and I'm also still associated as a data scientist with Histogenics, which makes it a bit easier to approach both parties for sponsorship. So I'll start with a small trip down memory lane. We won't quite go back to the age of the dinosaurs, but I would like, after last night's discussion, and so last night we had a very nice dinner and we talked about how people sometimes tend to reinvent the wheel, and we keep doing stuff over and over again in various areas of science and just life in general. These images go back to the end of the 19th century, when people had already been thinking about, oh, how are we going to capture microscopy data on one hand, and then how can we systematically move the field of view in very small, infinitesimal, incremental stages. And all the presentations my presentation at least, will be available online later, so there's not necessarily the need to take pictures of this. A video recording of my talk will be available as well later on YouTube, so again, I can just sit back and enjoy.
Show it to your kids.
Yeah. Well, my educational background, a little bit. I have a bachelor's in computer science. I wanted to do something useful with my IT skills. I mean, not just go automate systems so that people could get fired or something, which seemed to be the hype at the end of the 90s. So I decided to do something else. I joined an exchange program, and I ended up at Kroll University in Alabama, of all places in the US. And there, after the exchange program, I got a master's in biological sciences. It's during the exchange program that I ran into some biology people that had problems with computation, and I started helping them out, and I'm like, oh, this is actually really cool. Nobody's angry at me because they get fired afterwards after I'm done with my job. So my work, I actually did wet lab science, believe it or not. My work involved the interaction between replication initiation and transcription termination through a mechanism called autonomous replication sequences in Saccharomyces cerevisiae in baker's yeast. And one of the pivotal moments in my scientific career now, looking back in retrospect, was in 2003 when I attended a talk by Manolis Kellis of MIT at Göteborg at the International Yeast Meeting. He talked about this. Back in 2000, we only had the yeast genome. We only had 17 million base pairs. We only had it of one strain, Saccharomyces cerevisiae. And Manolis Kellis here, along with a group from Washington University St. Louis, was instrumental in sequencing the other yeast species as well. And they could do whole genome comparative genomics for the first time. And he gave a keynote on that in Göteborg. And I was sitting there and just like, wow, this is so cool. I mean, you can scale stuff, you can compare stuff, and scaling is what a lot of work in digital pathology is about today. So all the way back then, I was interested in this idea of taking something and leveraging it to other areas. Once you have a bachelor's in computer science and a master's in biology, there's really only one thing you have to do. You get a PhD in bioinformatics. And I did that at Iowa State University in Ames, Iowa. Also, maybe not the most obvious place to go, but it worked out really well for me. I worked on network biology with plant systems, mostly Arabidopsis at the time. Actually, while I was at Iowa State, friends of mine in another department at Iowa State were working on assembling the maize genome, for instance, and all those maize, rice, soybean, all of those genomes came out around the time I graduated or just after I graduated. So comparative stuff was not really possible at that time, for plant systems at least. So what did I do after graduation? I joined a relatively unknown CRO in Belgium called Histogenics. That was in 2010. In 2010, they had around 30 people in Antwerp. Today, they have over 110 people. They have their own office building. They have 2 sites, one in Belgium, one in the US. And they're planning a 3rd site in China. So that was a pretty good pick of me back then to join. The challenge that I was given when I was hired at the time was to develop complementary bioinformatics activities to a mostly wet lab based portfolio at the time. So what they wanted to do, they wanted to start offering post-analytical services. And history keeps coming back, right? So Veer Lepersi, who's here present today, was actually the person that initially, back in 2009 or something, forwarded my resume to the people at Histogenic, like, hey, have a look at this guy. I think you might be able to use him. And so now, 8 years later, we're here, and she's here too, so which is nice. Fast forward, I was working at Histogenics. They were using scanners to do all their slides, and at some point we figured it was a good idea that, given my bioinformatics background, I also picked up some more of the real digital pathology material. So I went to Baltimore in the middle of Hurricane Sandy. We all remember that very well, the people that were there at the time. Hurricane Sandy, they made t-shirts afterwards. And there I sat in on a talk by this guy, John Tomaszewski. Some of you probably know him. And John Tomaszewski gave a keynote on digital pathology and bioinformatics. And again, I was sitting there in the audience, and this was another Manolis Kellis moment for me. I was sitting there at the audience like, whoa, you can do this. This is so cool. I mean, this was 2012, you know. Halo, Videofarm, nobody had really heard from those guys yet. If there was anything around back then, it was Definiens and ImageJ and custom code. So John Tomaszewski has really done pioneering work in this area, and I was really inspired by him. But pretty quickly I moved back to Belgium, and then, you know, all this bioinformatics stuff is really nice and stuff, but you look around at this Histogenics, and very quickly I noticed, well, you know, if there's this guy, some of you might recognize him. This is Jeroen van der Laak of Radboud University in Nijmegen, of course. He does image analysis, and he says, I want pixels. Well, that's not that easy, because you have this universe of scanners out there, and they all have different viewing software, and they all have different file format, etc., etc. So if you want to serve this guy, if you want to offer this guy pixels, well, then you really have to figure out a way to circumvent this problem first. So we spent some time at Histogenics looking at existing solutions. Definiens was too complicated. Videofarm was not mature enough. OpenSlide, well, you give a DLL file to a pathologist, what's he going to do with it? Etc., etc. So in 2013, we decided to just build something ourselves, and that's what Pathomation became. So Pathomation is essentially, it's a Rosetta Stone for digital pathology. It's like an OpenSlide ++++++. And it can read all these different file formats and then just offer one homogeneous interface to it, one viewer. And so today, all the pathologists at Histogenics, they use the Pathomation viewer. They don't use the panoramic viewer anymore, or the Aperio one or NDP View. No, everybody uses Pathomation now. It's nicely integrated into the LIS system as well. So you have a very smooth, very productive workflow. In 2014, I also joined the Vrije Universiteit Brussels, which is my affiliation today. At the University of Brussels at the time, so you start very small, of course, very, very humble. You start with slides, you put them in the scanner, you have digital slides. The initial use case for digital pathology in Brussels was a biobank. And this is recognizable from any institute around the world, of course. You have tons and tons and rooms of these, rooms full of these. Thomas has nice anecdotes about this as well, I know. And then they have a biobank, and of course you want other scientists to consult that biobank, to use that biobank. So they decided to put digital pathology to work there. In 2016, I organized the first CBW SIG. So if you're not familiar with the bioinformatics world, so ECCB, this event is the European Conference on Computational Biology, and they have satellite meetings called SIGs, which stands for Special Interest Group. And then CPW is Computational Pathology Workshop, of course. So in 2016, we had the first meeting, and so some of the usual suspects here. Here's Jeffrey Fine from Pittsburgh, Jeroen van der Laak, Raphaël Marie from Belgium, who also has a suite of image analysis software. There's me, and this is Michael Montalto from Try. I forgot the name of this company. He's not here today. I tried contacting him, he didn't respond. Last year I was in Prague at ISMB. So ISMB is the bigger international version of this event. And there was a keynote talk by Christoph Bock from Vienna. And he literally made the statement that imaging is the new omics, which I thought was a very strong statement. So I think digital pathology has a role to play there. And digital pathology should be picked up by the bioinformatics community as well. In 2018, actually earlier this year, they decided that the simple version is the grant ran out, but not just the project was complete, but we think we delivered something really nice there. We went from this to actually a rather comprehensive ecosystem of digital pathology applications. We now offer applications for education, including a mobile app for the students, which is very nice. Like you walk in the morning, you administer an exam, but before you walk in the exam, you see people actually checking the slides last minute on their tablet, which is pure job satisfaction at that point in time. Like you made something that students can actually use and like to use and want to use. We did a couple of research applications, of course, mostly the biobank itself, which is how the whole project started. And then also here we helped some people organize their workflow, as in, they were taking screenshots from a viewer and then trying in something like Paintbrush to put a grid over it and stuff like that. Yeah, obviously that's not very productive. So this guy who we helped automate his workflow, he went from 8 hours to analyze the sample to 2 hours, which is very impressive. You don't see 400% speed ups that often. If only we could get those numbers for cancer survival or something as well, but we're working on that. So where are we now? Well, obviously we're in Atlas today, so 2 years ago I was still relatively new with the term computational biology. Today, however, everybody's using it. There's at least half a dozen events this year that tout like, "Ooh, come to us, we have computational pathology." But we actually have the person with us who first coined the term back in 2008, right? Mm-hmm. Correct me if I'm wrong on that, but that's the reference that I found. And Thomas, I'm very proud of having you here today, because 2 years ago, when I was organizing the first event, I remember thinking, I also did a survey of the literature, and I found your material, and I'm like, oh man, it would be so cool to have this guy here. Yeah, but that's not, that was like a time dream of mine back then. So again, that's why I'm very proud to have you here today.
Well, where else should anybody be than here?
Well, I'll make sure to tell that to Jeroen. So, but it's. I mean, that's the other thing. There's a small rivalry going on this year between me and Jeroen van der Laak, but that's only coincidentally, because the conferences, the ECCB and the ECP conference are overlapping this year. That doesn't happen every year. This is the first time it's happened ever since I've been following them. So, but yeah, other terms that are being used, everybody is always trying to come up with the next term. They talk about augmented pathology now, integrative pathology, histonomics, integromics, you name it. Everybody has a term for it. I think Chakra came up with a really nice term for it last year. But this is what it is to me. I mean, computational pathology, you use bioinformatics techniques and you apply them to digital pathology, and you don't reinvent the wheel, and that's how you can make the field progress faster and better, and learn from others and make fewer mistakes, hopefully. And then, February 2008, this was the first mentioning of computational pathology. But as Derek mentioned yesterday, we've been doing computational pathology for longer, of course. Last year at ISMB, somebody showed work from the 1980s where they were talking about, where they were using computer modeling to model limb development, budding limbs. So that was digital pathology all the way back then. They just didn't call it that way. And same thing goes for bioinformatics. We've been doing bioinformatics for a while before the term actually came about. Bioinformatics versus pathology. In pathology, you very much say, well, tissue is the issue. So you look at the topology and you detect different features in different types of cells, and based on their structure, for instance, the more homogeneous a tumor is, the more dangerous it is, etc. Bioinformatics, you very much take a different approach. In a lot of protocols, you grind up the tissue, you extract all the DNA from it, but your basic material isn't the topology anymore. It's more a smoothie like that, from which you then try to extract features again. And the challenge then is to bridge the experiments, right? So how can these different groups on all these institutes help each other? Well, you get a smoothie like this, you run proteomics or a few years back microarrays on it, and you get noisy data like that, and then you have to make sense out of that. And so the whole idea of this workshop is to raise awareness of the idea that, well, wait a minute, guys, there's all this topological information available already that could help you understand this kind of results. And so if you combine the toolboxes from both fields, the idea is that you get at least a more layered smoothie, and would help you make sense of the expression data, like, this side could be disease tissue, healthy tissue, patient stratification, better predictive markers. I mean, this is something that histogenics is very big on and constantly searching for. So here's a concrete example from 2 years ago, from the conference actually. They looked at CD30 cell grafts in Hodgkin's lymphoma. And they used, this goes back to my PhD work, they used network biology to study this. So they scanned the tissue, of course, and then they identified and labeled all the different types of cells. And then if the cells were close enough to each other, they decided to connect them with an edge. And then they did analysis on that. That's all described in the paper. That's all published now. But then I was talking to the guy afterwards, and again, based on my background, I was like, well, why don't you use something? You have your network. Why don't you just use another platform, a bioinformatics platform like Cytoscape? Because you go to Cytoscape, you go to the plugins, and you have all these great tools for network analysis, and you can move really fast with that. And they had never heard of Cytoscape before, so I decided to get in touch with the people from Cytoscape, and I asked them, look, I have this very simple data set. It's just coordinates. It's node 1 is at position X, position Y. So it's not more than that. It's a CSV file. It's 3 fields. And the answer coming right back like, oh, I don't think anybody's ever done that. So we made a plugin. Actually, Agros, the guy that wrote the plugin, is here today. So we made a plugin. You can now import this kind of data into Cytoscape. This resembles a well, and a well on a 69 well plate, and every dot obviously is a cell in the culture. And now you can do network analysis in there, and you have all these tools available. And all it took to make that happen was a couple of hundreds of lines of code, and then polishing and making sure that people couldn't enter silly values like negatives and stuff. But
is this a two-dimensional embedding or just raw data in XY locations?
Yes, this is just
not
raw
an
data.
embedding of this high-dimensional graph in the two-dimensional space. So there are no properties of the graph that were studied and then embedded on the.
Yes, there are. There are external because the raw file. But I knew that was possible. The raw file has an XY coordinate, and then for every marker, there's also an expression value. This is fluorescence data coming out of a BD fax.
So when you connect the edge, were you putting some weight on that edge? Or
on the nodes, they were labeled for each node.
Not on the edge.
Not on the edge right now, but I think that was actually an extension that I asked for because it is a useful thing to have. Now, I think Cytoscape can compute things like distances anyway.
Okay.
And like one of the things that we are able to do with the plugin now is to say, only define edges, because you can turn this into a fully connected graph, of course, which is pointless. So one of the things you can do in the plugin now is say that
not for
only
the physicist here in the audience.
Yeah, well, we can continue that tonight. But yeah, so one of the things you can do now with the plugin is say that if they're really close together, don't bother defining the edge. And if they're, you can kind of define a sweet spot. Like if they're too far from each other, don't bother. Like, don't connect this cell with this cell, but only connect the cells if they're within a certain radius.
Can you provide your own triangulation?
I'm sorry?
Can you provide your own graph?
Not currently.
Right.
Because it's also, there's a lot of stuff you can do with Cytoscape itself, based on its properties, and
So it's got lots of different ways of doing it.
yeah, exactly. So we
want these graphs as well, but it'd be interesting to do some.
This has like Y graph in it, so you could import this, define your edges based on distance, and then replot, use a different layout algorithm, for instance, if that to see if anything comes out of that. So it's a very exploratory. It's a very explorative platform. We didn't put too many features in the plugin because then at one point you run the risk of trying to outsmart Cytoscape, which is never a good idea, or actually reinventing Cytoscape. And this was really just a bridge to get the data from A to B.
Sorry.
I just want to ask about boundary conditions. So is there some way to address that? Say that there's this negative space that cannot be accessed, and
that's not added on.
Otherwise, you're going to get boundary effects.
Like for instance, there's this cell, there's this one right here, right? This is actually not a spec on the screen, but this is obviously something that got misrecorded. Now, as long as you're doing your pandas import in Python, for instance, you won't pick this up. This kind of stuff is maybe by chance, maybe if you really think about it. But this is something that you typically wouldn't pick up, and just by by easy visualization, you can immediately see that, oh wait, there's something wrong with this one because it doesn't fit in the website. So are we there yet? Well, I think 2018. There's still a lot of low-hanging fruit to pick. I think there are still big divides. It still amazes me that you go to API, you go to DPA, and everybody stands there like, oh, we have to go talk to the bioinformatician. You have to go to the bioinformaticians. There are only a subset of those people here today, so it's a little. It's actually hard to make that bridge to convince people to convince people to get out of their comfort zone. Is my experience anyway. I think adaptation is actually a lot slower than expected of digital pathology. And I think the exceptions are here, right? I mean, Pittsburgh is an exception. MSKCC leads, those are exceptions. In practice, adaptation is rather slow. There are still a lot of hurdles to overcome with the incompatibilities. This was a slide used in 2012 by the Finians to illustrate the problem. This is your image analysis, but there's a whole wall of practical considerations to overcome, to climb, to actually be able to get to data mining. Another example another advantage, for instance, of the styloscape set is that you have your imaging data, and now you convert it into a graph space, which a graph structure is a lot smaller, a lot more condensed, a lot easier to work with than all those pixels. Assuming your initial segmentation went right, of course. But this was done on a BFX machine. I mean, this is technology that we've been using for forever, that's been around for forever. I mean, for certain protocols, we just know what works, and it just does work. I was, and again, I accidentally stumbled upon. I was writing about all of what I'm saying here, and I accidentally stumbled upon a colleague of Shaka, and I was all excited about this, and I got the email back. Well, students don't begin from scratch in my lab. They enjoy a wealth of tools and code written before them. I mean, that's actually nice. But I think the next step needs to be, well, give us the tools, right? I mean, don't let everybody begin from scratch. I mean, I talked to one person at API a few months ago, and I asked him, what do you use? I use OpenSlide. Wait, why are you still using OpenSlide? Wait, there's other stuff than OpenSlide? Well, yes, apparently there's these people that have this wealth of tools and code, and what, you don't know about this? I mean, that's a challenge, but that's a general challenge of bioinformatics. I mean, there have been, in the last couple of years, there have been keynotes given about this problem. Like, some graduate student writes a program, it compiles with the option that he knows, then he graduates, and if you ever want to use it, well, good luck chasing down the student, and then good luck if he still remembers what he did like 10, 15 years ago. So that's a challenge. But that's hopeful, at least, that within certain environments you don't have to start from scratch anymore. You don't have to figure out the structure of an SVS file anymore, or an MRXS file. You can start at a higher level. And like I said, much work is still needed, and I think the tool developers in this room will only agree with that. So how can we attempt these issues? By making super duper user-friendly software, of course, but also attend a workshop. So I would say, okay, check. But there's a couple of things. There's 3 takeaway messages that I would like to give you, and that's first, don't build software for a single scanner. It's still very much about the file formats. You need to get to the pixels, as Jeroen puts it very simply. And the best way to do that is you build your software on digital pathology abstraction layer. There's
Jeroen's one as well. What's it called?
What?
Jeroen's got his own abstraction there as well. I can't remember what it's called. Lots of people using it. I want to put it in.
I don't know, use OpenSlide.
Yeah, well, I mean, OpenSlide is the one that's been around forever, of course, but it's very quiet on the mailing list, and Perk and Elmer recently came out with a new scanner that they're pushing very hard, and OpenSlide is becoming increasingly harder to rely on just with all the new technology. I went through the whole thing. I went through basic Pascal, C, C++, C#, Java. I've never come across a language where I was able to accomplish so much in so little time, both in terms of learning the language and being able to do stuff with it. Now again, scikit-learn has its pros and cons. Shakra can say more about that, but you can get stuff done at least. I mean that's amazing. That's a huge benefit. So I import. This is our own viewer. I import the package to read the files. I have a function that determines whether there's tissue in a specific tile in the slide or not. And the outcome of this is something that looks like this. So if it's a white space tile, I get a very simple histogram. If it's it actually has tissue in it, you get a more complex tissue, a complex histogram rather. And then based on that information, you can actually make a heat map of the whole slide to show where there's tissue and where there's no tissue.
You're only showing regions of interest, but it's a whole image.
Yeah, exactly. And that's just a few lines of that's 18 lines of Python code in this case. So that's really neat. Don't reinvent the wheel. You can still improve the cars, obviously, but don't reinvent the wheel because that's been done for you already. Network analysis, the example that I gave, I think that's a good one. Cytoscape plugins for digital pathology. If anybody's interested in building upon that initial thing that I made, you're welcome to have the code. I mean, there's nothing there's nothing proprietary about that, and we certainly won't have time to build a very user-friendly, nice-looking plugin slide on top of everything else we're doing already. I think there's a lot of potential to expand the current artificial intelligence and machine learning environments. There's something called Azure ML Studio from Microsoft. It's a point-and-click environment for machine learning. What 15 years ago, I took a machine learning course. It took me a whole semester to just grasp one algorithm and implement it. Now I can compare ensemble to decision trees to SVM to whatever in like half an hour just by pointing and clicking at it. Now that has its dangers, of course, but the point is that the environment is really user-friendly and you can reach out to a lot of people and get to use the software. But Azure ML Studio completely goes haywire. It's completely not useful once you get to imaging data. The imaging data is converted into a 2D array, of course, which is then flattened to a 1D array, and then those arrays are fed into. So you kind of end up with a digital version of the smoothie, right? And you lose your features, and so I think there's a lot of stuff to be done in this space because deep learning is hot. It's just that we don't have any good tools to address it. Contribute content, tutorials, presentations. How about a data camp or a Coursera MOOC on digital pathology? How about somebody in this room? Thomas, I'm looking at you. You have the biggest resources. But how cool would it be to talk to Pavel Pevner at UCSD for a new section at the UCSD Bioinformatics curriculum on Coursera? It only takes 8,000 hours of labor to make a good MOOC, according to him, by the way. So, and the first question for Pavel was that what do the normal mortals in this room have to do? But it's possible. I mean, it's there, and again, it goes back. Don't try to contact Coursera directly and say, hey, I want to do a MOOC about digital pathology. Talk to the people that have material on there already and leverage on top of that.